Hi guys, today we're doing titration curves. Now, syllabus outcome is investigate titration curves and conductivity graphs, which we're going to do next time, to analyze data to indicate characteristic reaction profiles, for example, strong acid, strong acid, weak base, and weak acid, strong base. So, a little bit of revision. The burette and the pipette are washed with the solutions that you'll be using in them. Okay, so we don't wash with water because if the water beads on the side, it will affect the concentration. So we wash it with the solution we're going to be using, so that if there's any beads left, they'll be of the right concentration. Okay, we usually wash it 2 times. The equivalence point is reached when there is a faint color change, super faint, okay? The slightest blush of pink from phenolphthalein, that's the point of our change. And 3 titers need to be within 0.1 mil to be considered accurate. Now, this is a titration curve. It's a plot of pH, which is our dependent, versus the amount of titrant added, which is our independent. So on the bottom on our x-axis, as we increase the volume, we measure the pH. So we're changing the volume of titrant added, analyzing the pH. That's what it looks like there. So we start off, in this case, we've got a low pH, so we're starting off with an acid. As we add base, it slowly increases, then there's a sharp jump, and then it slows off again. Out of interest, that's what we call a sigmoidal curve. Okay, it's got that nice sharp jump. Titration curves are used to monitor the reaction flask during a titration. So realistically, what we can do is we can plot the volume and pH and graph it, and from that we can then figure out the equivalence point. Okay, it can be a lot more precise than our indicators, because sometimes indicators, to actually change an indicator, it's a chemical reaction, and so that can affect our endpoint a little bit. So we can do it a bit more precisely with our pH probe. Now, 3 main types of titration curves, which are the ones that we were listed in the dot point. So they're strong acid with a weak base, weak acid with a strong base. Now each of them has their own particular reaction profile and also their own particular equivalence point. Okay, so they're not all going to be at an equivalence point of pH 7. Some of them are going to be a bit different due to the weak effects and the equilibrium stuff that goes on, but we'll get to that shortly. So strong acid, strong base titration curve. So here's an example. pH rapidly increases near the equivalence point. When I say rapidly, it's over the course of like a couple of drops. It can increase several pH points. Okay, but the main thing is that the equivalence point is halfway up that rapid increase, and for a strong acid, strong base, it will be 7. Okay, so there's no weak acid, weak base effects to push the equivalence point up or down. It's at 7. So if we have something like HCl with H2SO4, they're 2 acids. HCl with NaOH, okay, strong acid, strong base, equivalence point will be 7. H2SO4, sodium hydroxide, equivalence of 7, because they're both strong. Okay. Now, strong acid, weak base, it's going to be below pH 7. Okay, it's going to be different depending on the acid and base that is used, but either way, the equivalence point is halfway up that steep jump. Okay, so we basically find where the steep jump is, halfway up, that's our equivalence point. Okay. Now, the reason for it being below 7 is due to the effect of the weak base. Now, at equivalence point, the conjugate acid of the weak base reacts with water to produce some H3O+. So for example, ammonia plus HCl produces NH4 plus Cl minus. Now, because NH3 is a weak base, okay, some of those protons from NH4 plus will be donated back to water. Okay, and so this is what happens. So the NH4 plus donates it to water, which brings down the equivalence point. So even though we've added stoichiometric amounts, that equilibrium system is going back and forward. So it's producing some H3O plus at equivalence. Okay. Another very good system to look at is our acetate system. So CH3COO minus. So sodium acetate, if you just put sodium acetate into water, it will bring the pH down. That's because some of it goes back. Okay. Oh, sorry, no, that's the wrong way around. I'm thinking of the other way. But yeah, anyway, it's the same deal. So weak acid, strong base, it's going to have a equivalence point above 7. Okay. So in titration between a weak acid and strong base, equivalence point is above 7, but again, it's always halfway up the jump. And that's the important part. So we want to look at that steep rise, go halfway up, and find our equivalence point. Now, the reason for this one is that above 7, so at equivalence point, the conjugate base of the weak acid reacts to produce OH minus. So and this is where the acetate comes in. So acetic acid and sodium hydroxide produces acetate ions plus sodium ions plus water at equivalence. Now, the acetate ions will then accept protons from water, producing OH minus, which increases the pH. Okay, so this is a very good system to look at the opposite direction. So this is a weak acid, strong base. So this is why at equivalence, that sodium acetate is going to be basic. Okay, and like I say, if you add just straight sodium acetate straight to water, it's going to make it slightly basic because that acetate ion will absorb, will accept protons from water, leaving the OH minus. Now, weak acids, weak base titration curves, I did forget to change the title, but this is supposed to be weak acid, weak base. They're not part of the syllabus because they're very hard to use. Okay, you can see this here. This is a weak base titrating in a weak acid. Look at that lovely jump. Okay, if we're looking for halfway up the jump, there is no real jump, and that's why we really don't use them. Okay, it's also the equivalence point won't always be 7. It could be 6 or 8 or 9 or 4, whatever. It all depends on the weakness of the acids and bases that are being used. Now, how do we read the equivalence point? So we've been saying this whole lesson, halfway up the jump. Okay, what we then do, we find that point halfway up the jump, and wherever it is on the x-axis, wherever that point is, that's our equivalence point. So here's an example. This is one that was followed with a pH probe. Okay, we can see that nice jump. We measure off the top and the bottom of that. Okay, where it starts to increase rapidly. So before that point, it's not increasing rapidly. I mean, it's starting to increase rapidly, but it hasn't started increasing rapidly. But we mark out this top and the bottom. We halve that, so halfway up the jump. That is the point of our equivalence point. We then drop a line straight down to the x-axis. So in this case, if we read it, I know it's very small, but it's 10 mils. Okay. So we read the burette volume on the x-axis. Now, as seen, different titrations have different equivalence points at different pHs. Now, the best indicator for the titration you're undertaking is one that changes close to the equivalence point of your reaction. And it's possible to have a choice of several different indicators. Now, this is where, so we're taking a bit of a step away from the titration curves, just looking at indicator choice because of that whole, looking at strong, 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 weak, weak, strong. So, as long as the indicator has its endpoint in the jump, then it's okay to use. Okay, even though the endpoint might not be at the equivalence point, the difference could be so minor in volume as to not really affect it. So in this one, we've got a strong acid and a strong base. The equivalence point is 7. But having a look at that large jump, both phenolphthalein and methyl orange are suitable indicators. Now, typically we use phenolphthalein just because it goes colorless to pink. It's such a stark difference that it's just so easy to see. Okay. And typically we go acid into base for phenolphthalein, just because it goes colorless to pink. It's a lot easier to see than pink to colorless. Another practical consideration is detecting the color change. So like I was just saying, some color changes are not as easy to detect. That's why with phenolphthalein, we typically go colorless to pink, because that is a super, super different change. Like, it's so completely obvious when it starts to change. So in summary, titration curves are a function of pH versus volume of titrant added. Strong acid, strong base have an equivalence point at 7. Strong acid, weak base have an equivalence point below pH 7, and that's because of that equilibrium thing with the weak bases. So we get some of the weak base donating protons to water to give us H3O+, makes it slightly acidic. Weak acid, strong base, same deal. We have the conjugate base of the weak acid accepts protons, which pushes it above pH 7, making some OH-. And lastly, the best indicator to use is one that has an endpoint at the equivalence point or close to it. But the most important thing is that the endpoint for the indicator is on the jump. Okay, it's on that rapid increase. Okay, that's all for today. Thank you.